You have been reading challenges? Challenges?
Yes, sir.
All right. So any challenges? Please also remember that you are free at any time to post your problems on the classroom. I've noticed that students don't post issues that they have in the classroom, which defeats the whole purpose of using the classroom to study. So we cannot discuss everything in class. So the classroom, after the class, if you have particular issues, you throw them in the classroom. Let's talk about them. So don't wait for another class session to discuss things that have been there for 2 weeks. So I do not understand. Yes, is it Karel?
Yes, sir.
Yeah, what's the issue, Karel?
So predicate logic.
Sorry?
Predicate logic.
Predicate logic. Did you read the material I put on predicate logic?
Yes, sir, but I
Sorry.
didn't understand very well.
Okay. All right. So probably you would have a session. I'll have a session on you during after the class so that we can work out your individual problems. Let's not talk about that during this session. Okay?
Okay, sir.
Unless it's a general problem, then maybe I'll get more elaborate information or notes and give you on predicate logic so that everybody can benefit. But if you feel that it's a bit personal, then we'll work on a one-to-one basis. So can we work on it after the class, from any other period after this class?
Yes, sir.
All right, good. All right, any other question? Any other worries? Yes. Sets. Okay, booking seats. Yeah. The idea of booking seat is under predicate logic. It's just probably what she's saying. In predicate logic, generally you have a variable. You can only determine the truth value for a particular expression if you know a particular value for a variable. For example, if I say this seat, let's say this is seat 1, for instance, in front of me. If I say seat 1 has been booked, now you cannot know, if I say a seat has been booked, you cannot know if the seat has been booked or not if you don't know the particular seat. So you must know that seat number 1 has been booked. Are you getting it? So until you know the seat number, you cannot determine if it is true or false. So that statement is a predicate because you cannot ascertain if it is true or false without you substituting a particular value for that. So if I say book is seat S is booked by person P, you cannot tell me if this statement, this proposition, I'm using now book, I could have said B, SP, where B stands for that the seat is booked. It's a predicate. Remember, we use letters to represent predicates. And letters in capital letters is predicate, while those in small letters will be propositions. Okay? So I could say B stands for the statement that seat S is booked by person P. Which means that you cannot tell whether this statement is true or false unless you know what S is and you know what P is. So if I say that, let's say Peter is, okay, let's just presume this is seat 1. If I say, for instance, what is P of 1 Peter, for instance, it may be true. If it's true, then I'm saying that Peter has booked seat number 1. Are you getting it? And I'm saying that Peter is a person. Obviously, P is a person has booked a seat, and 1 is a seat. So it means that this statement now, as it stands, is a proposition because you can actually tell whether it is true or false because it's a real scenario. I've substituted some values for the variables. But book SP is more general. And we also said that you can actually cause a predicate to become a proposition by using those quantifiers. And we mentioned the for all quantifier and there exists quantifier. So which means that this statement book SP, I can change it to become a proposition by using either for all or there exists, or even a not to make it not to become a proposition. So if I say that for all S, B of P, then I'm saying that all seats have been booked, which will either be true or false. It's now I've quantified that statement. So the answer will either be true or false because I'm now saying that it's all the seats here booked. And if we look at it, you will see that all the seats are not booked. Then I can now say that this statement is false. Or I could say that does there exist a seat such that S of P, is there a seat that has been booked by somebody? That's what it means. There exists a seat such that, yeah. So I think maybe we'll get back to some exercises on predicate logic. I'll try to get maybe some videos so that you can follow for those who are having issues. Yeah. All right. So later I will try to explain to you later. I don't want to start writing on this online. You might slow us down. Let's just see what we can do. All right. So today we are going to chapter 3, and in chapter 3 we are looking at something called induction and recursion. Induction and recursion. I'm certain that you would have learned induction sometime in school. When you did mathematics, sometime you hear something like proof by induction. Yeah, so induction is a very, very powerful technique which you can use to prove that a particular mathematical expression or a statement is true. So remember, we have been given statements, logical statements, and now I want to see how to deduce or how to prove that certain statements are true or false, or certain compound propositions are true or false. And some of the proof techniques that we'll encounter, you have the direct proof method, you have proof by contradiction, you have proof by counterexample, and other methods like the proof by induction. So the proof by induction is a very standard method. If we give you an expression and say proof by induction, there's just one way of doing it, so it's not confusing. Now with the direct proof you might have to reason and start with a particular premise, and then use that premise to establish the proof. With the proof by counterexample, you just need to, it's actually used to disprove. Generally, counterexamples are used to disprove a statement. If I say that all Cameroonians are tall, then that statement, is it true or false? For you to determine if it's true or false, one way is that I could come with a counterexample. For instance, I can say that I'm short. Okay? Now, if I'm short, it means that I've been able to prove that there exists an instance where that statement is false. Therefore, the statement should be false. It's not true. So with counterexample, once you have one instance or one example that can disprove that statement, then it means that statement is false. We'll also look at proof by contradiction, and then we'll look at the induction technique. So generally, what are proofs? Proofs are simply logical arguments used to establish the truth of a theorem or a theory. Theorems generally are more of mathematical stuff. Theories are more of maybe some concepts. A theory of evolution, theory of population growth. They're just some statements to advance why things happen in a particular way. Those are just theories. But a theorem is a mathematical statement which has been proven. That's a theorem. For example, you know of the Pythagoras theorem. You know, which other theorems do you know of? Theorems. Sandwich theorem, okay? Yeah, the sandwich theorem. All right, so theorems generally have been proven. So in this section, we'll not be really dealing with proving things like theorems, but how do we look at a particular statement, a compound proposition, and see if we can determine if the statement is true or false. So the first technique we'll use is the direct proof. I don't know if, are you guys following here from the screen? You should have the notes are there now. Download the notes if you don't have internet, so it's easier to follow. So the first type of proof is a direct proof. Let's be on the same page. Listen, Dual, are you on track?
We are listening to you, sir.
All right, good. All right, so with a direct proof, what happens is a direct proof starts with the premises and proceeds by logically deducing or by a logical deduction until the required conclusion is reached. So for direct proof, what is important is that you start with a premise, and then you are going to use that premise to establish the truthness of that statement. So let's look at an example. The example we have here is, let's look at a simple statement that prove that the sum of any two even numbers is an even number. By the way, is that statement true or false? Do you think if you add two even numbers, you have another even number?
Yes.
Yes. It's true, right? Yeah, but if we ask you to establish a mathematical proof, remember, it will not, the human brain is very powerful. You can almost intuitively just say something is true or false. But if I say prove that mathematically, then you need to come out with some formalisms that you use to establish that. Now, in the direct proof method, we said you have to come out with a premise. So you have to start with a premise to establish any proof. So in this particular case, if x is even, what will be the premise? We are saying that x, the sum of two numbers, is even. Therefore, we are saying that if x is even and y is even, then notice that x can be written as what? 2 times any integer number, 2m. So if something is even, then it can always be written as 2m. Let me just write on the board for this one. So we want to prove that the sum of two even numbers is even. So the first thing we'll let a and b be the two numbers. The two even numbers. Now, if those numbers are even, then what you can say about a is that what? A must can be expressed as 2 times some n, where n is any positive integer. Are we there? If something is even, then you must be able to express it as 2 times n. And also, b should be expressible as 2 times some m, and m is a positive integer. Now, I'm not using n again here because we're not saying that the two numbers are the same. We are saying that they are even, which means that m and n may not necessarily be the same number. I'll just do the same thing here so that those who are following from Douala. All right, so what I was just saying is that if we assume that a and b are the two even numbers, then what we are saying is that a should be equals to 2 times some n, where n is an integer or a positive integer, and b as well should be 2 times some m, where m is also a positive integer. M and n do not necessarily have to be the same because they have not said that the two numbers are equal. You have to be careful. So the premise in this direct proof approach is that if a and b are even, then a should be equal to 2n and b should be equal to 2m. So these are the premises that we are going to use to establish the proof. Are we there? Is it true that if a is even, then it's equal to 2n? Some people don't know even numbers. Even numbers are numbers like what? Positive even numbers. So on 1, 2, 3, 4, and so on. I could be saying positive integers, some people don't know. So positive integers are numbers like 1, 2, 3, and so on. Okay? Are we there? All right, so we are looking at the direct proof here. I'll just put direct proof. All right. So what do we want to prove? These are the premises that we have established. Sorry, I wrote 3m here. Nobody is correcting me over there in Douala. I put the wrong thing and nobody. All right, so how do we now proceed? Show that the sum of two even numbers is even. So we have to sum the numbers, right? So we now say a plus b will be equal to 2n plus 2m, okay? And see that, and that L is still a positive integer. Which means what? Which means what? Therefore, what can we conclude? If a plus b is equal to 2 times some L, where L is a positive integer, which was like the premise that we used to know that something is even. Therefore, what can we say? A plus b is even. And we have been able to establish a proof. Do we see it? So we say that the sum of two even numbers is even. We took one even number and we said for it to be even, then a had to be 2n. And for b to be even as well, b had to be some 2m. And then we sum the number and saw that it gives us the same form as any even number. Therefore, our conclusion is that a plus b is equally even. That's clear, right? Kara, is that okay?
It's okay.
All right, good.
Okay, sir.
Yeah, all right.
Can you do it for odd numbers?
Sorry? Let's do it for odd numbers.
Yes, sir.
All right. So we'll just continue with another example. So this example says that prove that the sum of two odd numbers is even. Okay. Prove that the sum of two odd numbers. Or is it not? Yeah, the sum of two odd numbers is even. Okay, so that's what we want to prove. Now clearly, you can give two odd numbers and add, and you see that it gives you something even. So how do you go about it? Now, what is the premise? If A and B are even, are odd, sorry. If A and B are odd, then how can we express them? A will be written as what? Contributions. A will be written as what? Ideas.
CN.
C what? 3n.
Yes.
3n. If n is 2, then it's 6. 6 is not even, 6 is not odd. Contributions.
2n plus 1.
2n plus 1. That's good. Correct. That's good. Remember, if you add 1 to an even number, you get an odd number. It's as simple as that. Are we there? Yes. Where n is what? Is n an integer? N is still a positive integer. Right. Good. So that's what we get. And equally, we consider b is equals to 2m plus 1, where m is positive. Now, remember, there's nothing special about n and m in what I'm doing here. Don't think that n and m must be n and m. You can choose any variable. You can put q, z, and so on. What is important is that a or b must have the form 2 some variable plus 1 in this case, where that variable should be a positive integer. We specify that it's positive because if it's negative, I don't know whether to say negative 2 is an even number or not. So we are there on, we're trying to show that the sum of two odds is even, sorry. So if you add those two, you have this plus 1. And 2m plus 1. And if you sum that, you have 2n plus 2m plus 2. And that should give us 2 into n plus m plus 1, which you can see that has the same form as 2 to the 2l. Okay, where l is that n plus m plus 1, and it's also a positive integer. Remember, if you add two positive integers, you have another positive integer. If you add 1 to the positive integer, you still have a positive integer. Therefore, that thing there is equal to 2 times sum, which implies that, well, it doesn't imply. Therefore, the sum of two odd numbers is, no, it's therefore, it is not equals to, so be careful. Don't equate everything. So once you have that 2 to the L, you can immediately conclude that therefore the sum of two odd numbers is even. Yeah. Are we okay? All right. Those in dollar, is it okay?
Yes.
All right. Okay, so that's it for direct proof. Direct proofs are usually straightforward. You just start with a premise and then you use that to establish other things. There's an example there which says that Prove that if x is any number of the form 3k plus 1 for some integer k, then x squared is also of that form. So if x is of the form 3k, x is of the form 3k plus 1, then x squared is of the same form. What do you want to prove? We're required to prove this. If this is this, then this is this. That's what that question is saying. Does it look like it's difficult? It's just to multiply and rearrange now. Alright, so we'll do those ones when we look at the tutorials. Let's not spend a lot of time on the things that are. Is there anybody who will not know how to multiply those things? Okay, just spend 5 minutes and see if you can come out with that proof. It's right there now. Is there somebody that will not look at what is there? Prove that the sum of an even and an odd number is odd. So those are direct proofs. So you should know what you want. You should first of all start by establishing the premises. If something is even or something is odd, what does that mean? And then from that, you now use that to establish the proof. I think that A is even and B is good. All right. So okay, I think I'll just, for the benefit for those who are not sure, I'll just do it quickly on my screen. So I'm assuming that A is even and B is odd. Then see that I can express A as 2 times some n, where n is a positive integer, and B is some 2m plus 1, where m is a positive integer as well. Now notice that m and n are not the same. If you use m down and m up, you have it wrong, because you're actually saying that one number is one greater than the other. So, but it's arbitrary because you can deal with 2 and 21, 2 and 6, and 2 and let's say 11. So it's not necessarily 2 and 3, 3 and 4, and so on. So you have to make m and n to be different. So the sum a plus b clearly will be 2n plus 2m plus 1. And you can immediately see that you can actually factor out 2 and have this plus m and separate the 1, which is 2l plus some 1, where l is n plus m and is an integer. And therefore, we conclude that a plus b is odd. Are we there? So it is supposed to be a plus. Yeah, so that's that. All right, I think we have done quite a lot of direct proofs. So we can ask you all kinds of things. Prove that the difference between two even numbers, where the first number is bigger than the second number, is even. The difference. Do you think is even? The first numbers will be bigger now. Prove that the difference between two even numbers is also even. Is it true? Subtraction, yes. If you take 6 and subtract 4 or 6 and subtract 2, you still have an even, right? Yeah, but the way you formulate it, you need to put some logic there. You need to see that this one is bigger than this one and all of that gymnastics there. You need to see it as you're formulating it. Prove that if you divide, there are all kinds of proofs there. You've seen the tutorial exercises, the things that we can possibly ask you. But what you have to do is to keep an open mind and don't memorize. When we ask you a question, don't start thinking that it's the same like the one in class. Are you there? Just look at it and see how you can formulate the problem. You can use a premise, come out a premise or premises, and use that premises to establish your proof. All right, so let's move to the next type of proof, which is proof by contradiction. Proving by contradiction. In this method, we assume that the conclusion is false and deduce a contrary statement. Now, since the assumption leads to a contradiction, we conclude that the assumption was wrong, and hence the statement is true. You see, contradiction can also be very confusing. So, we'll give you a statement, you will take the opposite of the statement, and then you work with the opposite of the statement, and then you find out that the opposite of the statement is false. Therefore, you conclude now that that statement was true. Okay? So I could start by saying that, okay, Nubia is let's say, Nubia is the president of CIB. We'll start with it. Want to prove that statement. Or Nubia is a boy. Let's say Nubia is a boy. So it is easier. So at least it's true. So how do we prove? Yeah, because the other one was false. It will end up false. Okay, Nubia is a boy. So we'll say Nubia is a boy. To prove it, we'll start by first of all saying that Nubia is not a boy. Okay. Then we'll prove, and after we continue with that premise, we'll end up now in the statement that that statement was false. We'll end up by proving that it is false. It is false that Nubia is not a boy. Therefore, Nubia is a boy. Are we getting it? So we start with the statement. So it's like a proposition. You want to prove something P, a proposition. What do you first of all do? You instead prove the proposition P, not P. And if you establish that this is false, then what can you say about P? P was true. So you negate something and then try to establish a proof. And if you get a false result, it means that the initial thing was true. These things are very specific. Now, what normally happens in a test or an exam is that when you ask a student to prove something, maybe by direct proof, and the student doesn't know the direct proof, the student now does counter example, or the student goes to prove by contradiction, or just cancel like this. It's correct, but that's not the method we have asked you to use. So the method is very, very specific. You want to see if the student can do a proof by contradiction. Then you apply the proof by contradiction principle. It is better to make the statement and you cannot continue. You get at least 1 mark than to spend your time using another approach. It's like when we ask students to prove using the laws of logic to prove something, some people started drawing truth tables. The law of logic is not truth table. We want to see the law. I'm using the Morgan's law. I'm using the idempotent law. I'm using this law. If you change the question, then we cannot mark it. Because we want to test that particular concept at that time. But if I just say prove the statement this, you can choose to use your truth table. You can choose to use the law of logic. You can choose to use anything. You can choose to use common sense and prove it. But if they have specified the method, then you must use that method. So I could say use a direct proof to show that the sum of two even numbers is even. Then I specify the method. You cannot go outside the method. If I say prove that the sum of two even numbers is even, somebody might use induction. It's possible. Because I've not specified the method. Are we getting it? But once the method is specified, you must follow the method. Alright, here we have an example which uses contradiction. That example, you have to look at it very keenly. It's very confusing. Alright, the example says that prove that if xy equals to z squared and x is less than z, then y is greater than z for any positive numbers x and y and z, x, y, and z. Prove that if xy is equal to z squared and x is less than z, then y is greater than z. So if we were to come out the propositional, write that expression using compound proposition, what would that be? If I use a compound proposition, how many propositions do you have there? I'm looking at logic, predicate logic. Sorry, propositional logic. I have the statement x, p is the statement xy equals to what? Z squared. I have another statement. Q is the statement x is less than z. R would be the statement what? Y is greater than z. So what do they want you to prove? If x and this, so they want you to say that if it's implying P and Q implies what? Are we there? That's what they want you to prove. That if this is this, if xy equals to z squared and x is less than z, then the right hand side, then y will be greater than z. Okay. All right, I'll just put this on your screen. So it's contradiction. So that statement, I could liken P to the statement xy equals to z square, Q to the statement x less than z, and R to some statement y greater than z. And we are left to prove that P and, so the inverted V, where do I get that? So I'll just put and there. So I cannot get the inverted V easily here. Okay, it's here. P and Q implies R. Sorry, I missed this thing is not there. So this is a statement that I want to prove, that P and Q would imply R. Just a minute, please. That's what we want to prove. So let's look at how it's attempt this one using contradiction. So we'll suppose that the conclusion is false, it's not true. In other words, we suppose that xy equals to z squared and x is less than z, but the conclusion is y is not greater than z. Y is not. So we are trying to work with this instead. So we are negated one side. We say that this doesn't imply this. And what is the negation of y greater than z? Y less than or equal to z. Are we there? That's the negation. If y is not greater than z, then y is greater than. If y is not greater than z, then it is less than or it is equal to z. So we have changed the question. So the question now is to prove that P and Q is not equals to, doesn't imply not R, or implies not R. So that's what we want to prove. And if you can show that this statement is false, then it means what? It means that the other one was true. All right. So how do we continue to establish that? The first thing is that from the statement y less than z, if you multiply both sides by x, if you multiply both sides by x, the last this other side, you have that xy is less than or equals to xz. You see that? So if you multiply both sides by x, and what can cause you to, what will give you the right to multiply both sides by x without changing the equality sign? So for those in Douala, the contradictory statement that we made is that P and Q doesn't imply, it's not R. It's not R, it's R prime. So R prime is actually equal to, yes, multiply both sides by x, actually be y less than or equals to z. So multiplying both sides by x, you have xy is less than or equals to xz. Yeah. And I'm now asking, what made it possible for us to do this multiplication? Remember, if x is negative, something is going to happen from your mathematics. If x is negative, can you multiply like this? If x is negative, if you multiply, the sign will change. Okay? So the only reason why we multiply and the sign did not change is because x is positive. And it was mentioned in the question that x, y, and z are positive. So it means if you do this kind of multiplication here, you must write here that. That's why you're able to multiply like that. Multiply both sides by x, you have this since x is greater than 0. If x can be negative or positive, then there's no way you can multiply. You can only multiply by x squared. You can remember some of your mathematics that you did for you to maintain the sign. But for us, we are sure that x is positive. So since x is greater than 0, I could have xy now being less than or equals to xz. Now, what can you see again? What do you see that you can factor out? Notice that xy is equals to what? Z square. So I can replace z square by xy. So I can have now that z square is less than or equals to what? Xz. And since z is positive as well, so this implies what? From this statement, this implies z squared is less than or equals to xz. And since z is greater than 0, remember from the statement there, since z is greater than 0, what can we do? We can divide both sides by z, and we get z less than or equals to x. So since z is also greater than 0, we divide both sides of the equation above to get what? To get that z is less than or equals to x. Which does what? Which contradicts Q. You see? Which contradicts Q. It contradicts Q because we have said that Q in Q x is less than z, but now we are saying that x is greater than or equals to z. Remember, you can always interchange your statements. So this one is equivalent to saying not so. Just change the direction. Just put this one first. So it's the same thing. So you see that those two statements are contradictory. So we started by negating this side, and then we work with that negation, that contradiction. And then now we are seeing that the statements don't tie out. There's a contradiction. Because x cannot be greater than or equal to z, and at the same time x is less than z. It means that x is just nothing, or z is just nothing. It's not existing anywhere. since there's this contradiction, since this and this contradict, the conclusion is that this statement is equal to R, not R. Have you seen it? Yes.
What if you choose the other one, x is less than z, and set it to work on it?
X is okay. If you start with x is less than z, yes, it could still go. It will still go. You will still apply. So you try to make x resemble. I don't know. It's the same thing. So let's see. Where are you? You started with R. Okay, you're here, and then you do what? You divide. How do you even go to this? You have to use this condition. Are you sure you're able to survive? If you use cure, you will not use this condition. Somewhere you have to use this condition. You have to use this condition. I don't think you will not succeed. Because if you divide by x here, what do you get? Y less than or equals to z, but this one is something else.
So how do you know if you are supposed to choose, if you are supposed to display y greater than z or x less than z? Because what you did was you decided
To negate this side, because it is simple.
y greater than z, you decided to use it and you said
Because it is simple. So, okay.
how do you look at that?
You don't. It's logic now. We cannot tell you. You negate one of the sides. Either you negate this side or you negate this side. If you have to negate this other side, this will be not P or not Q implies R. I know you have not. Maybe you came. You don't know this law. This law is what? What law is this? De Morgan. This is De Morgan. Not P and Q is equals to not P or not Q implies Q. It will be more difficult for you to work with this negation or this and this. Okay? And by the way, now it becomes an or, it becomes even more difficult. Since it's this or this, it becomes even more obscure. So the easier one for you is to negate the right hand side. It's easier. And if you negate this other side, the problem will become more complicated. But you should be able to come out with the same answer. You should be able to come out with the fact that the statement is true or false. So see, yeah.
I didn't understand the first statement that P equals to P is x, y
equals to z squared. Yes, that's from the question, Brian. That's from the question. So the question said. The question is.
That P and Q.
Can you see my mouse? Can you see my mouse?
Yes.
Okay, so what I did is that I was just trying to convert this question into propositional logic. So I identify the different components of the statement. I identify that there are three propositions involved, and basically see that xy equals to z squared can be considered as one proposition. X less than z is another, and y greater than z is another. So I wrote that statement in propositional logic form as P and Q implies R. Okay? Where P is the statement xy equals to z squared, Q is that statement, and R is that statement. So that's what we want to prove. We want to show that if this happens and this happens, then it implies the right hand side, which is R. Are you there? So how do we do this? We are not using a direct proof. We are using a contradiction. We are proving by contradiction. So we need to negate one of the sides. So we choose to negate the left hand side or the right hand side.
So how does P and Q implies R?
Imply is if then now. If then. That's the symbol for if then now, is imply now. They have said that if this is this and this is this, then this is this. So it is if then.
Oh.
You see it?
Yes.
Actually, I'm saying imply. Imply is two ways. If then is not really imply. It's not double implication. It's in one direction. Yeah. So we see that if you negate the R, then you'll be proving by contradiction the result. So R is the right hand side, which is the result. So if this happens and this happens, this will not happen. So we negate this side. And if we negate this side and solve, we see that it's a contradiction. It means that what we negated was not correct. We're not supposed to negate. It means that that statement was originally true. Since we have assumed that the statement is false and we have ended up with a contradiction, it means that the original statement P and Q implies R was true. Are we there? All right.
I'm there.
Yeah, okay, good. So you can read more details there. Let's look at, I cannot think of any other example. Let's look at, in the tutorials we'll look at other examples. Let's look at the third technique proved by counter example. Oh, my battery is running low. Proved by counter example. Okay. All right. So counter example is a very easy technique because what happens with counter example is actually used to disprove a statement. You want to plug now. It's used to disprove a statement. You push it towards the side now. So what happens is you just need to come out with one example to disprove. Then you have actually established that the statement is false. Now, if we say that the statement that the sum of two prime numbers is even, okay, then if you can show us that there exist some two prime numbers where when you sum them, the sum is not even, then you have disproved that statement. Okay? So if you have two prime numbers that you sum them, the sum is odd, then you have disproved the statement. That is all about counter example. The example here is disprove the statement that every natural number can be expressed in the form x squared plus y squared, where x and y are non-negative integers. That's their positive integers. So we are trying to disprove the statement, which means we need to come out with a counter example. So if you can show that, for instance, if 3 is an integer, you cannot come out with some x squared plus y squared such that 3 equals to 8, then you have disproved. So the first example is for 3. 3 is a counter example. In other words, we show that there is no non-negative, is that what they said? Yes, there's no non-negative integer x and y such that x squared plus y squared equals to 3. There's no non-positive integer. If you put x to be less than or equals to 1 and y to be less than or equals to 1, then you see that x squared plus y squared will be less than or equals to 2. Are we there? Yeah, if x is less than or equals to 1 and y is less than or equals to 1, then see that x squared plus y squared is less than or equals to 2. So it's not equals to 3. So it means that we have already found an example which disproves that statement. If you go ahead and use x to be greater than or equals to 2 or y to be greater than or equals to 2, then you see that x squared plus y squared is always greater than or equals to 4. So x squared plus y squared cannot equal to 3 in either case. Therefore, 3 cannot be expressed in the form x squared plus y squared. Now, since we have found out that 3, the number 3, cannot be expressed in the form x squared plus y squared, then we have found a counter example to the statement that every natural number can be expressed in the form x squared plus y squared, where x and y are positive integers. We have found an example already. So if I say that, disprove that the sum of two even numbers is odd, then you just need to tell me that if you take two even numbers, 2 and 4, for instance, you add, what do you get? You get 6. Since 6 is even, then I've already found an example, a counter example, which disproves the statement. You see it? So generally, counter examples are used to disprove statements. So when I say disprove the statement that this, you should already be looking for a counter example to disprove that statement. Disprove the statement that the sum of two prime numbers is prime. For instance, let me just see what you can come up with. Disprove the statement that the sum of two prime numbers is prime. Can we first of all list some prime numbers? Just don't put on no prime numbers. Very easy to say that this. Can we have some prime number? Yes. 1, 4. 4 is a prime number. 1. Okay, let somebody first of all define a prime number for us. A number that can divide 1 and itself only. Yes, so you can only divide two things, 1 and also itself. Alright, so you have said 4, but 4 can divide 4, it can divide 1, it can divide 2. So you can divide 3 things, so it's not a prime number. Let's take it chronologically. There's 1, there's 2, there's 3, there's 5, 7, 11, 13, 17, 19. Okay, 19, and so on and so forth. Yeah. Okay, it's not 9. We skip 9 is odd, but it's not prime. Okay, why is 19 not a prime number? Okay. Okay, it's odd. Yeah. Okay. So at least we have an idea of prime numbers. So can we say the sum of prime numbers of two prime numbers is also prime? 3 and 5. Okay, 3 and 5 gives you 8, and 8 is not prime. So that's just a counter example. It's as simple as that. So counter example is a very, very simple way of proving. But sometimes too, it can be very difficult if you cannot come out with a counter example. Because sometimes all the examples might just look like it's working. You might try and everything is working, but there's some one number somewhere that doesn't work. So you need to be able to decode that there's an example somewhere that is not working. If not, you might just conclude that this statement is always true when there's a counter example somewhere. So, but that's it for counter example. Generally, they are very, very simple exercises. It's just for you to identify some sample values that don't work. All right. So I think from there we'll look at recursion. I'm trying to look where is induction. We're supposed to look at induction. Proof by induction. Okay. I'd like us to do proof by induction before we come to recursion. So that let's just finish all the proofs. Proof by induction. So this proof by induction is usually used to prove theorems on natural numbers. And what is very interesting about proof by induction is that you can prove something. You can prove that the left-hand side of an expression is equal to the right-hand side of an expression without you, just by using some simple tricks. So you see something like, they'll tell you that prove that if you sum 1 plus 2 plus 3 up to n, you get n into n plus 1 over 2. If you have done arithmetic and geometric progressions, all those formulas, you are seeing now 1 plus 2 plus 3 plus whatever up to n equals to 2. Right? 1 plus 2 plus 3 plus 4 is equals to this. Now, notice that you may not know how to derive this formula, but nothing stops you from proving that this left-hand side is equals to the right-hand side. You see? I mean, if you're a guru in mathematics, you probably know that this is an arithmetic progression. And the formula to get the sum of an arithmetic progression is, I don't know if it's 2a or whatever. I don't even remember the formula. Okay? So, somebody will know how to work this thing out. But with proof by induction, you can prove any expression with the left-hand side and the right-hand side, even without knowing the formulas. So how do you establish a proof by induction? The proof by induction has 3 steps. The first step is you are going to choose some particular values, like maybe some simple values. For n equals to 1, what's the answer? For n equals to 2, what's the answer? And if those ones are true, then you will now go ahead to prove for the induction condition. For an arbitrary value, say k, is the left-hand side equals, you assume that for an arbitrary value k, the left-hand side is equals to the right-hand side. And then you go ahead to prove now that for another value k plus 1, the left-hand side is equals to the right-hand side. So which means that you have the induction condition, which is, that's for k, and then you now prove that it is true for k plus 1. So if we had a statement on the board, what will happen is that you are going to assume that this statement is equal to a proposition or a predicate, p of, let's say p of n. Okay? P of n is the predicate that this is equals to this. P of n is the statement that this is equals to that. Are we there? Which can either be true or false, right? Depending on value of n you put. But since we want to prove that this is equals to this, we want to prove that for all values of n. It's for all, it's not only for some. Because if it's for some, then there's already a counter example now. Once there's a counter example, it means that it's not equal to. But if we're asked to prove that 1 plus 2 plus 3 up to n equals to this, then we are saying that for all n, all natural numbers, p of n is true. And how do you proceed? We start with the initial condition by testing for p of 1, for instance. And what does p of 1 give us? P of 1 will give us, p of 1 is the sum of the first term. So please remember that this is a sum, we are summing. So this is like summing of I from I equals to 1 to n. For those who have done some mathematics, that's what is happening here. We are summing I from 1 plus 2 plus 3 plus 4 up to n. So which means that p of 1 is a sum from 1 up to 1. P of 1 equals to what? So in p of 1, the left hand side is 1. The right hand side is what? Put 1 here. You have 1 into 1 plus 1 over. Gives us what? 1 now. 2 over 2 times that is still 1. We also try for some, let's say 2. What do we get for 2? What is p of 2? Left hand side. If sum of the first 2 terms, 1 plus, okay, it's sum. So it's not just the second term, it's the sum of the first 2 terms. And what is the right hand side here? Right hand side, one nice formula, so we put 2 there. 2 plus 1 over 2. And the answer gives you what? 3. with them. So if you put any values for n, n1, n2, so you can test for two values. And then now what you do is that you now test the induction condition for an arbitrary value. For some arbitrary value, for k arbitrary, if we say that p of k is true, so we'll say that p of k is true for some arbitrary value k. Then what are we saying? We are saying that 1 plus 2 plus 3 right up to k is equals to what? Okay? So this is assumption. Without this assumption, you cannot prove. Why? Because you are going to prove that for n equals to 1 it is true, for 2 is true, for 3 it is true. You don't know where to stop. So you choose any value for k which is arbitrary, you assume that it is true, and if you can show that it is true for k plus 1, then you have actually shown that it is true for any value. Because this k was arbitrary, which means that this k could have been k plus 1, it could have been k plus 2, it could have been k minus 1, and so on. Which means eventually you have shown that it is true for every other number. Since this k is arbitrary, k in this case can be 100, in another case it can be 99, it can be 5 in another case. So when you show that it is true for, assume that it is true for k, and you can prove that it is true for k plus 1, then you have actually shown that it is true for all values of n, because k is arbitrary. So if this statement is true, then we are now required to prove that what? That 1 plus 2 plus, we are now required to prove that actually p of k plus 1 is true. If you want to show that p of k plus 1 is true, how do we proceed? Now, we actually want to show that the sum from I equals to 1 up to n equals to k of I is equals to what? K is what? N plus 1. This now becomes k plus 2 all over 2. So, what is this sum? This sum, sorry, this k plus 1 here. So this sum will be the sum from I equals to 1 up to k of I, okay, plus what? Plus the k plus 1 term. I'll actually remove the last, the k plus 1 term. You see? So I'm going to sum from 1 up to k, then I will now add the k plus 1 term there. It equals to k plus 1, k plus 2, over 2. So this is what we want to prove. I should put a question mark here. We want to show that this one is equal to this side. So which side should we tackle? Left or right hand side? Which side can we simplify? This one that has trouble. The other one is already simplified. So we need to see how to spread this thing out. So let's see that this thing like this is equal to what? You see, because this part like this is just the same thing. Sum from I equals to 1 to k. This thing like this is that. So we can replace all of this guy with what? K into k plus 1. Now we add that plus k plus 1 again. And we want to show that it's equal to this side. So we can put an equality sign there and start expanding. So this is, how do I expand? I see that I can factor out. Oh, I'm not making a mistake. K plus 1. So there's about 2 somewhere now. Okay, so I see that I can factor k plus 1 out. And then what do I have here? K over 2 plus 1. You see, you can factor out k plus 1 here. And k plus 1, what you get? So it is equal to this, which is just k plus 1. What's the common factor here? 2. So you can actually have. So you see that it's exactly equal to this side. Let me see those guys. These guys are here. All right. So those in Douala, what I've done is that I've assumed that 1 plus 2 plus 3 plus n equals to n plus 1 all over 2 is the predicate P of n. So all of that statement is a predicate P of n. And we see that if we are asked to prove this statement, then we're actually trying to prove that for all values of n, the statement P of n is true, or the predicate P of n is true. Are you there? So that's what we want to prove. We want to prove that for all values of n, P of n is true. Remember, if for a particular value of n, P of n is not true, then it means that that statement is false. It means that we are able to come out with some counter example to disprove that statement. So how do we proceed? The induction approach says that we test for some values, some few values of n. So for instance, I'll test for p equals to 1. And if p is 1, see that the left-hand side will be equals to what? Those in Douala, what's the left-hand side? 1 plus 2 plus 3 up to plus n. If you sum the first term, what do you get? Can you get me?
6.
If you sum the first term, it's not 6. No, not. So if, remember, this side, 1 plus 2 plus 3 up to n is sum. If n is 1, then you are summing just the first term, which is 1. So it will be 1. Okay, the sum of the first term from the left-hand side is 1. Now on the right-hand side, what do you have? You will have 1 into 1 plus 2. So there you have to do the maths there, divided by 2. And if you do that, you equally have 1. Okay? So if you plug in 1 in this formula on the right-hand side, you have 1. Which means that P of 1 is true. Brenda, are you there? Brenda. Is Brenda there? Kara, are you there? Okay, Brenda's mic is off. Brenda, are you there? Brian, what are those in class? Can you get me?
Not in class.
Okay, you people are all everywhere.
Yes.
Okay.
Some are in class, others are.
What are those? Who is in class? Lolita, are you in class?
Cornelius is
No,
in class.
sir.
All right.
Cornelius is in class.
All right. I'm trying to figure out why Brenda is not responding. She just opened the thing and went away.
Yes, I'm around.
All right. Yes, I was trying to ask. I was just trying to ask if you are following because you have been so quiet now. Are you following that for P of 1? The left-hand side is 1, and the right-hand side also equal to 1 after doing the math.
I'm trying.
So there's the statement 1 plus 2 plus 3 up to n equal to n into n plus 1 over 2. So summing 1 to n is the left-hand side, and this other formula here is the right-hand side. So we want to establish that that statement is true. The induction hypothesis says that you choose some values for n to show that it is true, and then you assume that it is true for n equals to k, and then you go ahead to show that it is also true for some k plus 1. So I've put in P1 and it's true. Now let's go to P2. The predicate for 2, for n equals to 2, the left-hand side will give me 1 plus 2, which is 3. Because P of 2 means you sum the first 2 terms. Are we there? And for the right-hand side, I will just have to plug into that formula. So I'll have 2 into 2 plus 1, and I divide that by 2. And if you do that, you will still get 3. I'm sure you get 3 because you have 2 times 3 divided by 2, which will be 3. Notice that if you try for P3, P4, P5, and so on, you always get that the left hand side is equal to the right hand side. But now, since since natural numbers are infinite, you cannot test for all numbers because the numbers will never end. So you test for an arbitrary value, for instance. So you assume that it is true for an arbitrary value k, and then you go ahead and prove that it is true for k plus 1. When you can do that, then you have actually shown that it is true for all values. Since k was arbitrary, k plus 1 is just anywhere. Alright, so I'll assume that P of k is true. It can be anything, it must not be k. And if that is so, then what I'm saying is that 1 plus 2 plus whatever up to k is equal to k into k plus 1. All of that divided by 2. So that's what I've established from that assumption. Now the last step is for you to prove that. So we are now required to prove that P of k plus 1 is true. Okay? And what is P of k plus 1? See that P of k plus 1 will be, the left hand side will be what? One plus 2 plus up to k plus k plus 1. I made it easier here. So it's plus k plus 1. And the right hand side will be, so in place of k, you put k plus 1. So it will be k plus 1 into k plus 2. All of that divided by 2. Can we see that? So what we want to prove is that this equation here, probably like, let's say this equation 3, we want to show that equation 3 is actually equals to equation 4. So from equation 3, we can see that 1 plus, okay, we can see equation 3 is equals to what? See that from 1 up to plus k is equals to what we had earlier here. So what we had here, so what we had in equation 2. Okay, so this will simply be k into k plus 1 divided by 2 plus k plus 1. That's what we'll get. And if you are to simplify this, what you just want to do is just factor out k plus 1 and see that you'll be left here with k divided by 2 plus 1. And if you further simplify, you have there k plus 1 into k plus 2, all this divided by 2, which is equals to right hand side, or equation 4. So we have actually shown that for any arbitrary value k, if p of k is true, then P of k plus 1 is also true. Therefore, the conclusion is that what? For all values of n, P of n is true. We have shown that for all values, all, P of n is true. Yeah, that's what we wanted to prove. We wanted to prove that the left hand side, where is it even? There is equals to this. We tested for n equals to 1, it was true. We tested for n equals to 2, it is true. We cannot go on testing and testing for all values on the number line. So we chose an arbitrary value k and assume that it is true. And we're able to prove that it is also true for k plus 1. Since it is true for any arbitrary k and for k plus 1, therefore it's true for all values of n. By induction, it is true for all values of n. That will be the conclusion.
Hey, so why are you removing it? You are copying.
Copying or reading what? the notes are there. I don't want to be saying the same thing in the note now. That where am I reading from? No, I'm not reading from anywhere now. The conclusion there is that, remember, we have followed the induction process. You start with an initial condition. It's called a base condition. You see there in the notes, the base condition. When n is 1 or n is 2 is a base condition. And then the next step is the inductive step for an arbitrary value of n, or k. So you choose an arbitrary value of n, k for instance, and then show that it is also true for k plus 1. So that's just how the induction happens. The working is even there. You can follow it up on the notes. The working is there. It's quite elaborate. Alright, I think let's look at this other example. Maybe it's going to help. It's an exercise. Prove by induction that n squared plus n is an even number for every natural number n. There was a very important proof that we missed in the notes. The proof of we have to use a contrapositive. I don't know if we'll still get to that. I think we'll revisit this at the end. So let's just continue this. Prove by induction that n squared plus n is an even number for every natural number n. For every natural number, it is even. So we want to prove that for all values of n. All values of n, n squared plus this is so we'll let P of n be the statement n squared plus n, and then we're required to prove that word for all values of n, P of n. That we want to prove for all values of n, P of n. So if we were to follow that, we'll first of all start by what is P of 1? P of 1, the left hand side is what? Okay, first of all, we need to say what is meant by P. Okay. If P of n is even, actually we can change that statement. Let's change the statement. It means that P of n is actually the statement that n squared plus n. So we can write it as 2 times some L now. It is even now. Yes. So at every point, when you see, we can write down this expression as 2 times some L. So we are saying that, okay, what is P of 1? P of 1, left hand side is what? Left hand side will imply what? 1 squared plus, which is 2, okay? Which is equal to 2 times 1, okay? It's even. These are written as 2 times some number. It's even. Would I even need to be bothering about separating like this? So here we're just trying to show that it's equal to the right hand side. So this is equal to this. So it's true. Actually, we are saying that P1 is true. It's 2, which is equal to this. Now, we can see test for P2. We must not go directly to the induction step. For P2, what do you have? 2 squared plus 2, which is 6. And see that 6 is equal to what? 2 times 3. And 3 is obviously a positive integer, which is true. P2 is true. Alright, so let me just try to formulate a problem for those in Douala. So we are formulating this exercise by saying let P of n be the statement n squared plus n is equals to 2 times some L, where L is an integer, it's a positive integer. Okay, that's what it means for something to be even. It should be equal to 2 times some L. So we start the initial condition or the base condition. We can start by testing if P1 is true. See that P1 will suggest that 1 square plus 1, which is equals to what? 2, right? And 2 can be expressed as 2 times 1. Therefore, P of 1 is true. Now you can try for P of 2. P of 2, we will have that 2 raised to the power 2 plus 2, which is 4 plus 2, which is 6. And see that 6 can be expressed as 2 times what? 3. Therefore, P of 2 is also true. Now we go now to the induction hypothesis that P of K arbitrary is true. So we assume that for n equals to K is true, and we get a statement that what? K square plus K is equals to what? 2 times some S, let's say S, or 2 times TL. You can still use L, there's no problem. Let's use L, okay. Yeah, so 2 times some L. So we now, no, that's all. Using S is not actually correct because this K is different from the N. Even though we are saying that K equals to N. Well, it's still fine, it doesn't really matter. So that's the assumption. So using the assumption, we see if we can prove that for K, N equals to K plus 1, the statement is true. Now for P, K plus 1, see what we'll get. We'll get that K plus 1 all square, so you put the brackets. You have to be careful with your brackets. Plus K plus 1. We want to show that this is equals to 2 times some L. So this will give us what? This will be equal to, let's expand this now. Is it K square plus 2K plus 1 plus K plus 1 plus K plus 1. So we're expanding. We're doing an expansion of here we are putting K plus 1 there. So we want to expand it. This is K squared plus 2K plus 1 plus K plus 1. Hope it at the end of the day we want to express our answer as what? 2 times something now. Yeah, so we should know what we want. So you have to regroup these things to have 2 times something. So I see us having K squared here. I see us having this 3K plus 2. So we need to I need to regroup so that I have okay. Well, I don't have to simplify yet because I have to use the assumption. What was the assumption that I made? The assumption I made was that K squared plus K is equals to 2L. So I'll go anywhere that I see K squared plus K and I'll put there 2L. See that this 2K that I have here, I can separate it into K plus K, or I can take this K here and bring here. So what I could have is that K, well, let me just replace. So K plus K is 2L. So what am I left with? I'll be left with this other 2K here, plus what? Plus 2. Do you see? So if I use the induction hypothesis, this one and this guy will give me what? K squared plus K gives me what? 2L. So I now have plus 2K and then plus 2. Which is equal to what? 2 times L plus K plus 1. Which is equal to 2 times some S. Where S is L plus K plus 1. And it's also a positive integer. Which now gives me that. And so L plus K plus 1, and it's equals to 2 times some s, where s is L plus k plus 1 and is a positive integer. So what has happened? So I've actually shown that p of k plus 1 is what? Is true, not even. I've shown that the statement is true. I've shown that p of k plus 1 is true. I've shown that it is true. Duana, are you following? Just be looking at it. Let me see what we have here. Do like this. I'm not leaving through the window. Some of you need to come here with moon jackets. Moon jacket that in space. You come with my God, just like an astronaut. Rocket science. Please lost here. Let me see those who have lost the time. All these things that are about proof, about formulation, just tempting until it looks like what you want. So it's a funny kind of mathematics what you want. You are looking at an output, you know what you want, so you force whatever you have to resemble what you want. So if you are not creative, you are challenging for you. Well, we will not have to solve 1 plus 1 equals to 2. So that 1 plus 1 will give you something. Figure out, make it look like some other thing. Exactly the same. You are still having for 1 equals to, you are still having since that time. Not an induction. The first one, the first. Okay, to the left side. Yeah, that's for k equals to p of k plus 1 now. If you look at how p of k is, you don't need to take any place that you see k, put there k plus 1. Any place that you see k, put there k plus 1. Any place that you see k, change it to k plus 1. You just get what you have there. That's what we have done. But now see that when you are solving from 1 up to plus k plus 1, you have to pass through k before going to k plus 1. So there's k there, and there's k minus 1, and there's k minus 2. So those ellipses that we have there represent so many numbers. But we're interested in k and k plus 1 because you see that from 1 up to k, you can represent it as k into k plus 1. I think the way I did it online is easier. At the end of the day, I'll put the videos online. You can actually see how I'm typing the stuff. Sometimes the way I do it online is a bit different from what I'm doing it here. So, but for that, for the sake that some people don't go home so lost, maybe I should come back here. So what I did there was that for pk, we said that if pk is true, then 1 plus 2 plus 3 plus k is equals to this. Now I want to prove for pk plus 1. So I want to actually show that 1 plus 2 plus 3 plus k plus, no, after this is exactly k plus 1. It's equals to something. So anywhere you see k here, replace it with k plus 1. K plus 1 plus 1 is k plus. So this is what we want to prove. We want to show now that this is equal to this. Before, I will just write it like this. There's no difference between this and this. The only problem is that I've not written k here. That k is part of this ellipse. But remember, within this space, some other person might choose and have 3 plus 4 plus 5 plus k minus 2 plus k minus 3 plus plus k minus 1 plus k plus 1. So the same thing, because the person is trying to list almost all the terms. Right then, But see that at the end of the day, this one like this, up to the 1, will boil down to this term, which is all equal to k into k plus 1/2. Then the only thing that you do, you have to add is k plus 1. This induction step is very, very important. You must use it in this step. If you don't use it in this step, you cannot get anything. But if we came here and we refuse to use that step, then there's no way we'll have 2L here. Which means that we'll have an expression that we'll not even know what to do. We'll have k squared plus 3k plus 2. We'll finish. So we'll not even know what to do. We'll just be like we're in space. Huh? So you must use the induction hypothesis in order to simplify the expression to get p of k plus 1. It's time? It's time, okay.
It's time.
Alright, that's good. I'm happy that you guys are respecting time. I also need to respect time myself. I have to be somewhere too at this time, so I'm happy. So those who are here, I don't know if you take attendance. I'll just take the attendance for those who are here. So probably what I left out was, okay, there's an example which is very, very interesting, which I would like you to look at, is the example that says, prove that if n squared is even, then n is even. If n squared is even, then n is even. So if you try to prove that, you'll see what you see the challenges that you have. Try to use a direct proof. So just to guide you so that you don't go and split hair, try to split your hair. Well, I want you to show that if this is even, then n is even. So
And proof is not true.
using the direct proof. So with the direct proof, normally you say that n squared equals to some 2m now. And then you try now to prove for n. And then you get stuck. So you just get stuck here. You have a square root of 2, square root of n, you're finished. You cannot do anything. Yes, you're just lost. You no longer be in real algebra. You no longer go about discrete mathematics because the square root of 2, square root of n. So then what I want you to know is that this statement, for instance, if n squared is even is a proposition p or the predicate, and n is even is a predicate here, then what we want you to prove is that what? Okay? Are you there? So what we want you to prove is this. Now for contradiction, we showed that this was false. We proved that this was false, therefore this is true. Okay? Now, another way of doing this proof is to change this statement into its contrapositive expression. Which means, if we ask you to prove that n squared is even, then n is even, you can actually change this to, okay? And we saw that the truth table for this and this were what? The what? The truth table for this and this was what? I'm writing the answer already and nobody can tell me. Logically equivalent. Yes. Logically equivalent. Which means what? Which means that if I ask you to prove this and it's not going, if this can go, then it's the same thing. Because these two tables are logically equivalent. So if you get stuck at this step, what you can prove is that if n is odd, then n squared is odd. If you can establish this, then you have established that one. If you can establish a contrapositive of that statement, P implies cure, then you have also established that for cure, not cure implies not P. If you can establish the contrapositive of this statement to be true, then this statement is also true because they are logically equivalent. Well, is it true? They are logically equivalent. Question. So actually in that exercise, if you try to prove that n squared is even, implies n is even, you get stuck. You should not conclude that it's false. If you look at the contrapositive, you see that you'll be able to solve it out. Because if you try to use some examples there, you always see that when n squared is even, n is also even. You always see that. But now when you use a direct proof, you get stuck at some point. Alright, so those in Douala, before you round off, so that's your homework. Your homework will be to look at that question there, which is somewhere in the notes there, which says that if n squared is even, then n is also even. And what I want you to note is that if P implies Q, this statement is equivalent to what? To the contrapositive. Okay? Not Q implies not P. So what I would like you to use is, when you try to solve this question, this homework question, using the direct proof method, you see that you run into problems. But when you apply the contrapositive, so that's the contrapositive, when you apply the contrapositive of that logical expression, you see that it will be possible for you to prove the statement. And since from the laws of logic that we learned is that the statement and its contrapositive are logically equivalent, therefore, if not Q implies not P is true, then Q implies Q is also, P implies Q is true. Alright? Alright, so those, I hope you have noted your attendance. I'm going to use that from the portal to note those who are present. So any questions, please post on the classroom. Don't wait till the next class before you post your questions. If I come to the next class and you have a question, then you'll be considered absent. So post your questions on the classroom and we'll discuss from there. Are we good? Are we good? All right, good.